So we prove that if function have a good smooth, then its Fourier transform have a good decreasing. Yes, the smoother function, the faster it decreases to the zero. And second theorem, the inverse property. If let function lies in L1 and x belongs to L1 too. So function decrease faster, yeah, because x is increase, but this multiplication again lies in L1. F have a good decreasing. Then Fourier transform is differential. Have a continuous derivative. Okay? Proof. By definition, Fourier transform is this integral. And formula, formula derivative. Just formula because we don't know why we can take a derivative inside the integral. So what we can say about this function? This function has a majorant which is integrable by this property. So by Lebesgue theorem, by corollary of Lebesgue theorem, if we have for any parameter y, first this function is differentiable, yes, on y. This function is differentiable on y. Differentiable. And this derivative has a majorant from L1. Then, by Lebesgue theorem, we can do it. Then we can do it. So, by Lebesgue theorem, just this not formally, but it is real derivatives, correct derivative. If function is differentiable and this derivative has majorant from L1, then we can take derivative inside the integral, dy. I omit this. I forget it. dy. This is we can differentiate this. So by
there is no like a Weierstrass or Weierstrass theorem related with this one. It is not from Weierstrass or Weierstrass.
No, it's Lebesgue theorem. It's corollary of Lebesgue theorem. Standard Lebesgue theorem. Standard Lebesgue theorem. Fn goes to f almost everywhere and exists function g from L1 such that Fn less than g. Then lim integral of Fn d mu equals to f d mu. You can take the limit inside the integral. You can change the integral and limits. But derivative is a limit.
Okay, yeah.
You can consider Fn as fx plus 1n minus fx divided on 1 over n, for example. They tends to the derivative, yes, almost everywhere. And we have a majorant. And we have the majorant. So we can do this derivative. Okay? And again, by induction, what you can prove? What is modification of this theorem? xg, g equals 1 to k. If it's preserved, it's can multiplicate it up to power k, then it's have k derivatives. Then Fourier transform have k derivatives. It's continuous derivatives. But if you have such decrease rate, then you have a smoothness of.
If we only have j equals to k, that is not correct.
What?
If we only have if we only have xk, fx belongs to.
And if you have first power, we have one derivative.
Yes.
If it is integrable with all these powers,
It has to be with
then
all-
the Fourier transform have k derivatives, continuous. This just the last the last power, the largest power of x. So we have k derivatives. And question: do we have a space where smoothness and velocity of decreasing? In what space we have both a good increasing and a good smoothness? Schwartz, yes, Schwartz space. Schwartz space. S capital. Just I again consider only one-dimensional situation, but you can of course consider the function of many variables. But it's more technique, more difficult only in technique. It is function f which of class L infinity first, and for any p q equals n and 0 such seminorms supremum of x powered p f powered q is finite. So all derivatives decrease faster than increase any power.
What is the n?
Natural and 0. Natural and 1.0. The typical example of function from Schwartz space.
Exponential.
This exponent. Because in one on semi-axis will be increasing. And this is a decrease on both semi-axis. And it is smooth, of course. And it is smooth. But one problem, I take definition. F exponentially decrease if exists positive number a such that f of x belongs to L1. Then we name this decreasing exponentially decreasing. Of course, this function is exponentially decreasing, yes? But in definition, we have only power of x decreasing. From theorem 1 and 2, what follows? What do Fourier transform with space S? Function have so many derivatives as you want, and all derivatives belongs to L1 by this property. So the Fourier transform decreasing faster than any power. And again, you see that function decreases faster than any power. So Fourier transform have so many derivatives as you want. So Fourier transforms. Yeah, we take function from Schwartz space and put again in Schwartz space. But it is B action in this space. So from L1 to C0, it is not B action because it is not surjective operator. But this, it is B action and it is continuous operator. But unfortunately, this space is not normed space. It is not no, it is not no norm.
Schwartz space.
Schwartz space is no norm space. It's not Banach. It's complete metric space. You can write you can write a metric because we have countable seminorms. Countable many seminorms. You can write a metric. So, but it is we study theory of operators in norm space. But we just try to prove that it is B action and it is continuous. First, I define two operators in S. First operator D, it is df, it is E d, like impulse operator, or momentum. Moment. And operator MF is XF, coordinate. Theorem. Sorry, how you can define the continuous function in locally convex space?
I think it's called semi-norm space.
I don't match it. I might it only, but I think it's only Helmsky used. But I like this terminology, semi-norm space. How you can determine the or define the continuous of operator? Examples. So let's something general notation. You have X linear space and set of seminorms in this space. Convergence. We say that xn go to x if for any alpha go to 0. We have it is a sequential approach, but you can write a topology approach. You can introduce a topology. What is topology in this space? What is the base of topology? Base of topology do you have a topology as a course of topology or not?
In this course?
Yes.
Well, kind of.
Differential geometry and topology.
Base of topology, so you x0 p alpha 1 p alpha n epsilon. It's so-called standard ball. Standard ball in semi-normed space. What it means? It is such x small from x capital that p alpha e x minus x0 less than epsilon. For e equals 1 to n. What you can change? You can change epsilon, you can change the seminorms, and put together its topology, base of topology. And arbitrary open set is the arbitrary union of such balls, standard balls. And then you can define the continuous operator in topology sense. So if you say, if you have one semi-norm space p alpha and y with q beta semi-normal space, and you have operator A from x to y is continuous if for any q beta from here, q beta ax, exists constant c p alpha 1 p alpha n, such that for any x from x, q beta ax less than constant c sum p alpha eta of x.
The definition finite
Of course. And this set, constant c, and this set defined only by seminorm q beta. Not depends on x. If you have only one norm in both spaces, you obtain the bounded operator. Yeah. If you have only one norm here, constant c, norm here. It's just a definition of bounded operators. But we have a lot of seminorms. So we must, for any seminorm, obtain the estimations with finite linear combinations. It's easy to see that these operators are continuous in S, in Schwartz space. Because what you can say about this? It is just we have only additional derivative. So it is clear that this operator is continuous. And what you can say about this? xq xfq. Yes? But by Leibniz formula you can obtain that it is equal xp plus 1 fq. All derivatives goes on f, yes? Plus q x pi f, and one derivative go here, and here goes q minus one derivative. No? And that's all by Leibniz formula. This term only zero derivative or one derivative. Second derivative equals to zero. So it is less than f p plus 1 q plus q f p q minus 1. That's all. So it is continuous. What is why these operators are useful and important? Because with this operator we can calculate Fourier transform without any integration, only changing letters. A theorem. We have following commutative rules. In S. We have following commutative rules.
Can you explain here the second term? The second term is supremum.
What?
In the supremum, the second term. Yes,
Here.
Power k, q minus 1.
Because Leibniz formula f g nth derivative equals to Cn binomial coefficient and the following sum. But the second derivative of x equals to 0.
Yes.
So we only can take all derivatives go on q, all derivatives q. And then q minus 1 derivatives on f and one derivative on x. and other terms are zeros. So we have only two terms. And that just by supremum of sum less than sum of supremum, it's just semi-norms in this space. So I think it's sufficient only prove this part, yes? For inverse Fourier transform the same, but only the changes of signs. So I only prove this. By definition, it's x f of x, yes? And by definition, and we can take derivative inside integral, because our function decreases very fast, yes? So, and they differentiable. If I take derivative by y here, here not x, but after derivative, and d it is equal ed, it is with imaginary unit, yes? Operator d is derivative with imaginary unit. So, I 1 squared 2 pi fx minus ax e an exponent. And you see that I minus I equals to 1. And we see that the same. It's just coincide. So you see that it is just the same. And the second, fd f equals to this integral d e f prime and integration by part. This is 0 because our function decreases fast. So it is 0. And this you see that it is just I minus I is 1. And here minus, so we see that it is minus y square root 2 pi f e minus ex I dx. So it's just minus m f hat, yes? By integration by part, so we obtain the second. Continuous operator and B action. This continuous operator and B action. Well, let's try to prove it. First about continuous. It is not easy, but if I change what I want to define a new system of seminorms in this space, but equivalent. What we can say about, for example, I can consider one space with one set of seminorms and the same space with another set of seminorms. And you want to define the properties that the set of seminorms are equivalent. What it means? The set of seminorms are equivalent. We can operator of embedding this space to this space is continuous. And the inverse embedding is continuous too. Or you can rewrite it as the following. For any q beta exists C1 alpha 1 alpha n such that q beta of x less than C1 sum p P alpha eta of x for any x from the space X. It is one embedding. It is operator of embedding in this direction. And again, for any P alpha exists C2 beta 1 beta m such that P alpha x less than C2 Q beta e x e from 1 to m for any, again, x from x capital. It is an inverse embedding. So if we have these two estimations, then these sets of seminorms are the same, are equivalent. It is a definition. So let's introduce new f p q1, 3 indexes. 1, it means I set something from the L1. It is not supremum. It is integral of xp f q derivative dx. Before we have a supremum. Just now I consider this the same object, but in L1 norm. Statement that it is equivalent to our old system. It is equivalent to our old system. Why? Because it is not difficult. Newton-Leibniz formula. Newton-Leibniz formula. Minus so you immediately obtain that the model can be estimated as what? As sum of absolute values of integrals, yes? Is it clear, this estimation? I take absolute value from the left side, so you take the absolute values on the right side. So you can put absolute values inside the integrals and then increase the area of integral. Okay? But what you obtain? You obtain just f p q plus 1 1 plus f plus p f p minus 1 q 1, and it not depends on x. Can I take the supremum? Can I take supremum of this? Take supremum of x, so you obtain f p q less than f p q plus 1 1 plus p f p minus 1 q 1. So we obtain one side estimation for this definition, yeah? And second, well, that just I write this, what we can do. I can't take away supremum, unfortunately, because the identity one constant is not integrable on all space. Yes, it's on all axes. But what I can do, I can write it in following. interesting trick. I multiplicated on this and divided on this. And I take away a supremum of enumerator. FQ yep, but this is integrable, so it equals P FPQ plus FP plus 2Q. It's arctan, and the integral equals to pi. And this is an old system. So I obtain another estimation. So they are equivalent. So these systems are equivalent. And we prove the continuity of Fourier transform in S with help of two sets of seminars. They are equivalent. So we must, what must? We must to find the estimation of this. Yes? We must find the estimation for this. If we want to change the continuous of operator, if fx is S, we must say something about this seminorm, yes? It must be finite. We know that function is S, but it must be, must obtain the estimation with the some linear combination of seminorms. So but how you can write it with the help of operators M and D? How you can write it? How you can write this? Composition. Here M powered P. Here D powered Q. Imaginary identity doesn't matter because we have absolute value. And here we have letter F. So in one book of quantum mechanics, a good epigraph like that on some history part of quantum mechanics, the specialists of quantum mechanics became a man who only changed a letter. So just change the letters. We know commutation rule. We know commutation rule. So what happens with this? Yes, I transform from this and only change the letters. Okay, this is x p d dx, doesn't matter, I powered q, oh sorry, not, it is not correct. This, yes, mq first, then derivative. I can put absolute value inside. What you can say about this? Oh, sorry, it is not correct. Use again Leibniz rule. Leibniz rule of derivative of factor of two functions, of product of two functions, product of two functions. What you can say about x q f by Leibniz rule, it is sum from g equals to 0 cpg xq minus g q factorial on g factorial, yes? When we take derivative of this and fg. But it is constants, yes? It is different constants. So if you put it inside integral, what you can obtain it? It is less or equal. And what is the upper limit of this? Upper limit. For different functions f and g, you must write p. But here you have a polynomial. Some derivatives can be 0. So it's minimum between p and q. What happens earlier? The p ends or q ends. Some derivative of powers can be 0, yes? So then let's continue here. Less or equal some you can take the largest constant. Yes, this is constant, this is constant. It doesn't matter. You can take maximum from this. You can write c multiplicated on what? Sum for g of minimum pq, and here you obtain q minus g, g1, because we have inside the integral. Is it clear how I obtain it? Put this sum inside this. And by triangular equality, you write this, you see this multiplicated on this power, taking this derivative, but inside the integral. So it is semi-norm with index 1 in L1. So we start with this and finish with this. But it is that depend on y. So you can take supremum. So take this supremum on y, and you obtain that f p q less constant c f q minus g g1. What it means? It is a continuous operator. It is just a continuous operator, but we prove it with the not the semi-norms of this family, but with semi-norms with the equivalent family. So operator is continuous. Why it is bijection? Why it is bijection? The auxiliary statement. So we finish with this continuous bijection. Why it is bijection? Auxiliary statement, if some lemma, let f and g belongs to space, Schwartz space, and at some point f and f at x0 equals to g x0. And then and we have linear operator in S. A is linear operator and S, and A, it commutates with operator M. Then AF at point x0 coincide with this result. If two functions have the same values at point x0, and we have operator which commutates with them, then the images of these functions again have the same values at point x0.
The same, the last one.
What? This, yeah.
AF and AF.
A, sorry. G, of course. G. Of course, G. Is it statement clear? How we could prove it? Proof of this lemma. Consider function, this function. What you can say about value at 0? It is 0. Let's write Taylor expansion with piano residual. So h of x equals what we have? It is 0, so it is equal x minus x0 h prime x0 plus o small x minus x0. A Taylor representation with piano residual. Yeah. You can write it as this factor as follows. It's just operator m minus x0 identity. Just this. So a hx equals a m minus x0 I on this. Let's I write the following. I can take x minus x0 out the brackets. So I can have this factor, x minus x0, and I obtain O small of 1. But our operator is commutates with m. So how you can write it? M minus x0 I because we have this rule. We have a commutative rule. What you can say about this function? We know that this operator is linear from in S. So it is result is function for in S. It must be whole this in S. But this is not in S. That does this in S. This must decrease. So it is some function in S. It is some function in S. What you can say about the value of result of your acting at point x0? This is 0 because this is 0. It is just this reading. So we obtain our result. So we obtain our result. Yeah? This. Because operator is linear. So this is equivalent that AF at x0 then following. From this lemma we immediately obtain that operator A is operator of multiplication of functions. So if AM equals MA, then AFX equals to AXFX. It is just a multiplication of function. How we can prove it? From what? Let's take one point x and freeze it. So from point x, denote it as x0 and freeze it, stable, fix it, fix this point. What we know, if function coincide have the same values, the result of our operator have the same value. So what our operator is linear, but if I fixed one point, all my space, all my functions became constant. Yes, it is value at point x0. one-dimensional space, constant. How looks like operators in one-dimensional space? Linear operators in one-dimensional space. Multiplication on constant. So a f at x0 is constant f of x0. On what this constant depends? If different functions have the same values, the result have the same values. It just depends on functions. It depends only on point x0. So it is some constant a depends on x0. And we make it for fixed point x0. And now refreeze this point. Allow this point x0 changing. So you obtained immediately AFX equals AX FX. And now look on your what you write. Please commutate. What result of commutation will be? Yes? Look please at your table, at your papers. Is I correctly remember this? With minus. And commutate these operators.
That's correct, yeah.
Yeah, so what you see that this commutates with M. So composition of Fourier, direct Fourier and inverse Fourier is a function, yes? So we obtain that this, but now check this, please, commutations. F, M, F, D, F, F. So multiplication on functions commutates with derivative. What you can say about function? D is d per dx. It is derivative up to the constant. And multiplication on function commutates with derivative. What you can say about this function? This must be the same as this. You see that this part just the same as this part. So what you can say about the second part? 0. So A is constant. What we prove? Can you resume what we prove? It is up to the constant identity. Up to the constant is identity. And now let's, why I take y square of 2 pi erased. Let's calculate something. What is the Fourier transform of this function? Do you know that calculation integrals with residuals? Complex analysis. So we just do something with this. So I calculate, I don't try the constant 1 over square root of 2 pi. I just calculate the integral in Fourier transform. So just calculate this integral. I want square. I take the square, yes, I obtain the square of this. Here it is. Then I obtain the this on this, the double multiplication. Yes, it's correct. It's just this. But then I obtain additional term is the square of this with minus. So this is give us for A. Yeah. Imaginary unit in square is -1 and here minus. So it will be plus, but we don't have this. So we must multiply on this. But it is integral in complex plane, yes. It is integral on line in complex plane. We have x and we have integration of this, the I, y for A. But we need to integrate on real axis. What we can do? We can write some contour. Our function is holomorphic in this contour, yes? So no residuals. So the integral equals to 0. On these integrals, when we go from the origin, the fixed length of integral, yes? But x larger and larger. And we have exponent with minus x squared. So the integral on these intervals go to the 0. So integral on the real axis equals minus with this. So these integrals on this axis and this axis are the same. It's clear? So it is. So we can put away this. So this integral. So it is. New variable u dx equals du over square root of a. So we obtain and what is meaning of this integral?
Square root of b.
Or 2 pi. Who remember this integral?
Is 0 to minus infinity?
Square root of b.
Square root of pi. I obtain square root of pi. So oh, sorry. This is the result.
Why you wrote pi in the denominator here?
Oh. But we calculate only integral. And if I write this factor as an, then we obtain that and take a good value for parameter A. Please. You have C, you have this result.
1/2.
Yeah. So obtain that for this function, it is eigenfunction for eigenvalue 1. If A equals to 1/2. And then we see that if we take this factor for definition of Fourier transform and for inverse Fourier transform, we needed to obtain this. That it is identity. So it is B action. So it is B action. And moreover, what we obtain. Do you remember what is the norm of this? The estimation of norm as from L1 to C0. What was the estimation? We obtain this. This function belongs to L1. So, and so for this function, you immediately obtain the equality. Because functions doesn't change. And what we can do further, in what direction we can move. So we have one operator in two situations. We have Fourier transform in norm space from L1 to C0, and we have the Fourier transform in this space. This good situation because this norm space, but operator in this space is not good because it is not surjective. So it is inverse operator unbounded. Here we have a good B action and continuous operator, but these functions are not norm. They semi-norm space. Semi-norm space. But S is dense in L2. In L2R. How we can prove it? How we can prove this? Why S dense in L2? The linear combination of characteristic function is dense in L2. Yes, linear combination of characteristic function. So it's just a picture, but can you give some argument that this is real a function from S? So it is so-called smooth indicator. When I take epsilon smaller and smaller, it stands to the characteristic function of interval AB. So smooth indicator. Smooth indicator. How we can obtain? Let's denote this function phi A B epsilon. How it looks like its derivative? Zero something positive because function increase. Here 0. Here function. So-called it is a difference of two so-called head functions. Head functions like head. Can we construct a smooth heads? Can we construct a smooth head function? Smooth. I define new space. Maybe we have time next to consider some situation for distributions. It is not Schwartz space is S. I define new space D. It is function phi from C infinity R and it's continuous function which are smooth functions, have any derivative as you want, C infinity, but with compact support. complex support. So-called finite functions. Do I need to define what is support function? Is it known or not?
Differential geometry next.
You know support.
So in differential geometry,
It's closure of the set of points for which function is not zero. A typical example function from D, let's take psi x. This function looks like Of course, it is smooth function right to the zero and smooth function left to the zero. One question why it is smooth at zero, but it have exponential decreasing at zero. And you can prove by induction that it is equal to this polynomial of if you take a derivative, n derivatives, it is polynomial of degree to n of 1 over x multiplied on function psi. So this polynomial has at zero polynomial growth, yes? At zero it has polynomial growth, but this function have exponential decreasing. So by L'Hopital rule you can check that the limit at zero is zero. It is exercises on L'Hopital. Derivative of exponent is exponent, derivative of x goes to constant. So this function belongs to not to the and how looks like this function? It's just head function. This function looks here and then asymptotically to 1, and another function have another. So the product looks like this. So we have infinitely smooth functions, which looks like head functions. So we have this, so we have this. So that's why S is dense in L2. And now let's obtain important. Do you remember Parseval identity? For Fourier series. The square of norm equals to sum of squares of Fourier coefficients. Here we have integral Parseval identity. Let's take two functions f, g in S. We have this identity. The scalar product between Fourier transform of functions coincide with the scalar product of functions. Why it is so? Let's start from we can write this scalar product in the following manner. I write only definition of Fourier transform of f. But how we can write this? All functions lies in S, so we can change we can use Fubini theorem and change the order of integration. And you can write it like this. And first I integrate by y. It is not depends on y. What happens here? By conjugation, you change the exponent with sign minus to the sign plus. You have direct Fourier transform and inverse Fourier transform. And we know that in S it is a bijection. So it is gives us a function f. So we obtain the Parseval identity. And S is dense. So can you extend this operator, Fourier transform, on all L2? You can construct the extension of Fourier transform on all L2. And it will be unitary operator because we have isometry here. We have isometry. That's why I write this factor. So in physics, you write Fourier transform on the integral, yes? And the inverse with this factor, or not?
Yes.
But because in the L2 it is very good operator, in symmetric, so it is unitary operator. If you write different constants, it is not unitary operator, but it is unitary up to the constants. Up to the constants.
If cap also we write 1 by root 2 pi.
What?
1 by root 2 pi.
You write this?
In physics.
Right or not? Right.
We write,
Right. Here and here. Yes.
yes,
Ah.
1 by root 2 pi.
Daniel, not right.
Also, some different books with different.
And different look. I see. But we write this constant only to have the unitary. So we prove the theorem that there exists extension. So what we can do? We can do following. If function f belongs to L2, then exists sequence fn belong to S such that fn goes to the f in L2. We know that the S is dense in L2. Then we know that fn we prove the Parseval identity for function S. So this goes to f, so it is fundamental sequence, so it goes to the 0. So we immediately obtain that this is fundamental. Fundamental. So we can define as and this definition is correct because if you take another sequence, you can again construct new sequence which is interlaced. Yes. Typical situation. If you take another sequence, which is go to f. Yes. Then you can take H1 F1, H2 F2, Hn Fn, which tends to the f because Fn tends to f, Hn tends to the f. And by this property, you obtain that H1 hat, F1 hat, H2 hat, F2 hat, Hn hat, Fn hat have common limit. Yes? Have one limit. This sequence have the limit. So from this, you obtain that limit Hn hat coincide with the limit Fn hat. So because French, yes? Something like this. Exist unique. There. exists unique unitary operator in L2, which on intersection of L1 and L2 coincides with Fourier transform, with integral. Because of course by this rule nobody calculate Fourier transform. It is difficult. You must first you must find approximation in S, then calculate Fourier transform of this approximation, and then find the limit. But Plancherel's theorem states that there is unique, which on this spot, and for example on S, it coincides with classical Fourier transform. Because for function from L2, if you can see in textbook, you can see that for function of in L2, the definition of Fourier transform written as integral, but it is not good idea because for function from L2 it is not exist. It exists for function from S or for function from L1, but for function from L2 it doesn't exist. But you can prove that exists this in sense of principal value, in this sense, in the symmetric perimeter, this integral exists for function from L2. In the sense of principal value, if you take the limit in symmetric.
This is the right definition, right?
Yeah. So let's some examples. By the way, what is the spectrum of Fourier transform in L2?
Plus minus 1 plus minus I.
Yeah. How you can prove it?
Spectrum mapping theorem.
Yes, spectral theory. Because what makes the square of operator? Moreover, is it clear that Fourier transform have the inverse in L2? It has inverse in S and it has inverse in L2 because it is a unitary operator. Unitary operator, the inverse is a joint operator by definition of a unitary operator. What you obtain if you take the second power of Fourier transform? By definition, it is this integral, yes? But you can write it in the like this. So it is inverse. But at what point? At what point? Minus x. So you obtain f minus x. So the first power equals to identity. And we proved the lecture, previous lecture, I've proved the spectral theorem transform, yeah? So if you consider polynomial p of t for minus 1, so you obtain that the spectrum of p of f equals pair of spectrum of f. But it is equals to what? This polynomial of transform is zero polynomial. Yes? This. By this rule. Spectrum of 0 is 0. What can be spectrum of operator f of Fourier transform? we immediately obtain that the spectrum of Fourier transform lies in this set, plus minus 1 plus minus I, the zeros of this polynomial. Then you can, one we have obtained. Do you know system, Hermite system? Hermite. Functions. I hope it is correct.
Single D.
It is and then orthogonalization. Orthogonalization. Gram-Schmidt orthogonalization procedure. You obtain some polynomial I think can be a homework problem. Write first 4 elements of orthogonalization of this system. Was or not? Who remember? Do we have such homework problem? Write 4. Question, why 4? Why only 4? How many points here? We know that first function is not changed. Yes, it is just this function. And we know that Fourier transform of this function, it is the same function. I write the same value, arguments. This function is even. The next function from this system is odd. They are orthogonal. They automatically orthogonal. So the second function is this function. How we can calculate Fourier transform without no integration? Only changing letters. Because this operator M. We obtain the same function, but what is eigenvalue? Minus y, minus I. Next function is x square minus 1, 2, an exponent. Just do exercise yourself. And third, x cubed minus 3 over 2x. They change parity. It's all, even, odd, even, odd.
So
It's always.
H0, H1.
And
So the first function is H1, right?
this is the first function.
H1.
It's have eigenvalue 1. These functions have eigenvalue minus I. This function have the rule is following. It is number of function. Number begins from 0. Each eigenvalue have infinite multiplicity. Each eigenvalue, they are all eigenvalues, and each eigenvalue have infinite multiplicity. According to the residuals on dividing on 4. These all functions with number which is divided on 4 have eigenvalue 1. Which is have residual 1 have eigenvalue, oh, I sorry, picture is not correct. Because we check that it's minus I. So we have this direction of the circle, on the circle. So it is for minus, this is 1, this is 2, this is 3. And then circle. We have cycle. Okay. Moreover, the harmonic oscillator commutates with Fourier transform. Because what is harmonic oscillator? What is this operator? Oh, by F. harmonic oscillator, this operator, without any constants, right? You can write it as d square plus m square on f. Of course, it's because d square changed to the m square changed to the d square. So it commutates with the Fourier transform. So they have the common set of eigenvalues. So harmonic oscillator have eigenfunctions the same. They are mid functions. Eigenfunctions, they are mid functions for harmonic oscillator. But eigenvalues are the odd natural numbers. Yeah? Do you know this? Yes.
What do you mean?
1/2 plus this
2n minus 1. What?
the energy level, right?
It's actually
Or n.
half.
Or all factors.
No,
It's actually n plus half.
n plus 1/2.
It depends how you normalize here.
Yeah, something in the factors. Yeah.
It depends on for this.
So it's like 2n plus 1 by 2.
No.
N plus half means 2n.
The way to win is hanging.
They are positive because the quadratic form of this operator is positive. Of course, you see.
It's positive.
Positive, but in this normalization, it's all odd functions, odd numbers.
The factor. Some factor. In physics, you put 1/2 or something. Here,
They write this Planck constant. Without normalization, let's check on this, for this function, what we obtain. Harmonic oscillator on this function, what gives? The first derivative we obtain minus x e minus x squared. Yes, this is first derivative. Second derivative minus plus x squared minus x squared 2. Then you write minus two derivative for the positivity of quadratic form. So we obtain plus e minus x squared 2 minus x squared, and then you plus x squared. So this you obtain that it is 1 for 1. And then if I remember, then you can obtain for this normalization odd numbers. Okay, let's come back to this. Something reminds us of complex analysis. Calculate the Fourier transform.
Fourier transform.
Yeah.
Yes, we need to integrate with contour. Right?
Yes.
Expresses.
Like this half an exponential.
With all time, if we have a square, we consider we assume that a is positive for convenience. Then, if you write up circle, take contour in the half plane, but you need that on this part, on this circle, semicircle, this integral
Yes.
must go to the 0. Must go to the 0. So for what y it will we take complex numbers except x. So for example, in up half plane lies I minus I or I is 1. So exponent goes to the 0 if y is negative. For this contour is for positive y's. Here we have this residual. Here we have minus I, this residual. So Fourier transform equals 1 square 2, then 2 pi I, yes, and the sum of residuals. Sum of residuals. Here we have this residual I y divided on 2 I, y negative E. And here we have the inverse direction of contour, yes? So we have additional minus. So if we I go away, yes, square root 2 pi, we have something like this. Yes, we can write general formula. And in what space? This function belongs to L1. Yeah? If I write this function, it's not lies in L1, it lies in L2. You can write, calculate Fourier transform again with residuals, but you can write what? Function g equals x squared plus a squared. You can write g equals mf. So you can calculate Fourier transform very fast, again without any integration. So it's only sufficient to take a derivative by y. What gives us a derivative? The derivative of the Fourier transform of g equals square root p2. Exponent is the same, yes, it is exponent, but derivative of absolute value is sine. We obtain minus a sine y divided on a. So answer is and minus. It exists almost everywhere because derivative doesn't exist at 0, but we consider it as function from L2. You see, it is not a C0 function because this is not from L1. It is from L2, but this result is in L2 too.